we have met the unclocked SR flip-flop, and the only difference with what we are going to be discussing next is that the clocked SR flip-flop has the inputs to gates G3 and G4 modified such that the two inputs are not shorted, but these two inputs, this is not shorted and this is not shorted. These two inputs are fed with our clock pulse, and therefore when the S changes, the change is going to be effected or implemented by the clock pulse. So you will see a change in the inputs of our SR flip-flop, which now takes this form. That is, G3 and G4 have the inputs fed with a clock pulse CK. The only other difference which we will not discuss right now is that the G2 and G3 are fed with some clear and preset pulses that are used for presetting the initial state of our flip-flop, either being at 0 or at 1. But for now, we will not discuss this. We just understand the role of this clock pulse in our SR flip-flop. So before we discuss how the clock pulse amends the function of our SR flip-flop, we want to see that the clock pulse are coming in pulses of short duration TS, and therefore when we send such a pulse to our two gates G3 and G4, this gate, when the pulse has not passed, will not change state even if S changes from B0 to 1 or 1 to 0. But when the pulse happens, then it's like serving as a gate or turning on of this gate. Whenever we have this pulse come, and you can see there are many pulses. So every time a clock pulse, the gate input is now transmitted to the output. Remember we said that a NAND gate will always be a 1 when the clock pulse is at 0 or when the pulse has not been sent, and therefore the two gates will appear like they are inhibited or turned off, only displaying value 1 irrespective of what is at the input of Sn and Rn. So, but when this clock pulse passes, it allows the NAND gate to display the output dependent on what is there at the two inputs of G3 and G4. So that is the functionality of the SR flip-flop with a clock pulse. That is, when we set a pulse of a high, then this gate will give an output depending on what is at the inputs. If the pulse has not been sent, this gate will always give a 1 and irrespective of what Sn and Rn are. Having understood how the SR flip-flop works in the presence of a clock, then we can say that the characteristic table of the SR flip-flop will be the same as the one that we saw earlier for the unclocked flip-flop. No changes except that we are talking about the next state from the previous state. So this is what will change. That we are saying that if the previous state was Qn, we're talking about n being the present state. The next state is expressed as n plus 1. Then we are saying that when S is 0 and R is 0, the next state will be the same as the previous state. That is why we are calling it Qn. And again, we remind ourselves that we do not use this state of 1, 1, but for when S is 0 and R is 1, the next state is a 0. And when S is 1 and R is 0, the next state is a 1. We now talk about the excitation table of the SR flip-flop, and this is achieved the same way we were able to do the excitation table of the gates. We ask ourselves what will be the next state, or what are the required inputs if the present state changes from the current state to the next state. So this symbolizes present state and this symbolizes next state, and we can use Qn to symbolize present state and Qn plus 1 to represent the next state. We are asking ourselves what are the required inputs, and those inputs for SR flip-flops are Sn and Rn. So that is what the excitation table asks. If we want to move from the present state being a 0 to the next state being a 0, what should be our inputs Sn and Rn? Again, if we want to move from the present state being a 0 to a 1, what should we set our S and R to be? Similarly, 1, 0 and 1, 1. And we will get this excitation table from our characteristic table, which we said was given by S, R, and Qn plus 1. So this is the characteristic table that we have already made before for the SR flip-flop. And now we are asking ourselves, if we want to move from the present state being 0 to 0, what do we require? We can get that state from two possible combinations. That is, the previous state was 0, it remains 0, or the previous state was unknown and it will be 0 the next state. So these two rows represent the two possible situations when the next state will be 0. And that is, what do we require? We can clearly see that for these two states, we require S to be 0 in both cases, and R can be anything, can either be 0 or a 1. That is what we say, that we require S to be 0. There is 0 here because that is what is consistent. And since R is changing from 0 to 1, we are saying that we do not care what R is. And therefore, we give that the required input for R for the present state change from 0 to 0, then we say that Rn is a don't care. We look at another example where we are saying that we want to move from 0 to 1. So in this case, when we want to move from 0 to 1, we can only move from 0 to 1 from this input set. And I want to say that if the present state here could have been 0, or the present state could have been 1. So if it was 0, it remains at 0, then we are not able to work with this possibility that we are moving from 0 to 1. If it was 1, then it remains at 1. It has not made that transition from 0 to 1. So the only two inputs that gives us a transition from 1 to 0, or from 0 to 1, is when we have S set as 1 and R as 0. And therefore we say that we require S to be 1 and R to be 0. So again, we want to ask ourselves, if we want to move from the present state being a 1 to 0, then again we are saying that this could have been 0 or this could have been a 1, but we do not want to remain in the same state. We want to move from 1 to 0, and therefore this is the only input combination that allows us to move from the previous state of 0 from 1 to 0. And therefore we require S to be 0 and R to be 1. And assume we want to move from 1 to 1, with there are two possibilities. It was at 1, it remained at 1, that is 1. And here it is possible that it was at 1, it remained at 1. So we are going to use these two combinations or these two possibilities because here we are transitioning from wherever we are to a 1, and here we are remaining at 1 if we are at 1. And therefore, we are saying that we are going to work with these two possible inputs. And that means S can be anything, can be changing from, can be 0 or 1. But what we observe is that R is at 0. So what we say is that R must be 0, but we say that S is a don't care. And that is how we develop the excitation table of SR flip-flop. And now for the state diagram of the SR flip-flop, we want to simply represent that data that is represented by this excitation table in a diagram. We are saying we have two possible states. We normally represent them using circles. You have state 0 and state 1. So these are the two states. It is either at 0 or at 1. So if we are asking ourselves, we can be able to transition from 0 to 1 or 1 to 0, or we might be at 1 and remain at 1, or we were at 0 and we remain at 0. That is the first description of a state diagram. And then we ask ourselves, what do we require for us to move from 0 to 0? So we simply look at these times when we were at 0 and we remain at 0, and we simply say that the required input is that S should be 0, and we don't care what R is. So when we don't care, we don't even write it here. So for us to move from 0 to 0, we require S to be 0. For us to move from 0 to 1, we're talking about this transition from 0 to 1, we require S to be 1, this 1, and R to be 0, this 0. So for us to transition from 1 to 1, we were at 1, the present state, and we want to go to the next state to be at 1. So we are talking about this move. We are saying the required inputs are that Rn should be 0, and we don't care what S is. And finally, for us to transition from 1 to 0, we require this combination, and we are saying that S should be 0 and R should be a 1. So that diagram is the one that is called the state diagram, and again it's represented right here. So this is what I have simply described, that for us to move from 0 to same state, we require S to be 0, etc. So this is what we have just described on how to develop the state diagram.